Recording in progress.
Okay, good evening. So, a very short video in which I will show you something of the topic of the last video I have yet published on my YouTube channel. We talk about now ARTA software and how to measure impulse responses, and so how to calculate, to evaluate acoustical parameters. In particularly, we will measure RT60 and two acoustical parameters that are spatial parameters: the EACC, the interaural cross correlation parameter, and the lateral fraction. Okay, so ARTA is very simple, has a good help file, a good user manual, so I refer to the manual for an in-depth knowledge of the software. That is simple. It all is in the tools bar here. You see buttons for every function, for every type of measurement. So to record an impulse response in ARTA, we go here in record impulse response time record. This window opens. I can access to this also with this button here. Okay. Now I check in setup the audio device, the properties of audio device. I'm using a Behringer sound card, and I'm recording the signal in the channel 1 microphone. Okay, all looks okay, so I record the impulse response. Puffed. So we record impulse response here basing on FFT computation. So ARTA is not able to record directly in time domain. Every impulse response that you can perform in ARTA is an inverse fast Fourier transform of an FFT. Okay, so we choose the FFT. 64K is sufficient. I refer you to my videos on the topic. For this small room, is a small room with a microphone on table, also the speaker on table, just to see things moving. Okay, not special, anything special here. So we can record a sweep, pink noise, MLS, external excitation like the pop of a balloon, but always, I repeat, basing the computation on FFT sites. Okay, we record the sweep. Record. Okay, and so this is the impulse response. Now I can visualize of this the frequency response, DFT, the step response, the measure I have obtained has a good signal to noise ratio, obviously, little gain. So with these buttons here on the left, on the right side of the screen, you can manipulate the graph of the impulse response. So another things here that you can perform is the energy time curve. So this is the ETC, energy time curve. You can look at decays with some kind of graph like the cumulative spectral decay, very powerful, very interesting, and other things. What is interesting for now for us is the window for acoustical parameters computation. That is this. You can evaluate automatically the ISO 3382 acoustical parameters in a form of table, okay, with all the values here for in octave band or 1/3 octave band that are the resolutions required by the standard according the different type of application, okay. Usually 1 octave band is sufficient for many applications. You can choose also a graphical presentation in 1 octave and 1/3 octave of all the computed acoustical parameters. You can export, obviously, etc. You can manipulate the graphs. This is so the energy decay. This is the ATC, in which the Schrader curve is calculated. Okay, this slope of the curve can be set automatically or according to the necessity of the user. You can move here things to see the slope changing, and in this way you can change the way of how this curve go slowly in the floor of the noise. Okay, tendenzially auto is sufficient for many applications. There are also different algorithms for this. Check the manual for in-depth knowledge of this. Okay, the range of the impulse response, you can see the noise floor, so you can estimate the signal to noise ratio. Is a very good signal to noise ratio here. It calculates something of more 80 dB. Okay, and so this is simply the measure of the monoaural acoustical parameters that you can perform with an omnidirectional microphone that is, as I said, explained in my videos, lessons, etc., sensible to pressure component of sound phenomenon. No? And so you can see here parameters, the evaluation of parameters like C50, C80, early decay time, strength, T20, T30, etc. But following this simplicity in working of ARTA, you can perform also in ARTA in a very simple way the spatial acoustical parameters. If you go in analysis and click on spatial acoustical parameters, you can perform here measuring live or in post elaboration importing yet measured impulse response in stored in wave form, okay, in wave format. You can import also external impulse response to elaborate this. Okay, the parameters you can evaluate in ARTA, the spatial parameters, are the interaural cross correlation, EACC, and the lateral fraction. I refer you to my videos, my lesson and seminars on acoustical parameters for an in-depth knowledge of these parameters. I can say just that interaural cross correlation give you an estimation of the different reflective patterns of each ear. Okay, indeed, EACC is measured with the so-called binaural microphones like this. This is a Roland CHEP 100 euro, something like this, that you put in your eye, in your in your ears, okay, and so you record the impulse response. You obtain this way a stereo file with left and right channel. So a normal stereo recording with these two special microphones inside your ears. In each channel, left and right, there are the two different impulse response of your ears. Okay, so EACC, the interaural cross correlation, quantify the difference between the two impulse response. Okay, I say this in simple way. The patterns of reflections in the two inner channels are different. So the reflection caused by the ears, also the external ear, are different in each ear itself. The reflective patterns near the ears caused by your head is different from left and right side. Indeed, also with the binaural inside the human head, you can use special microphones that are head. And so you can use this special microphone to record the binaural impulse response you need to perform the interaural cross correlation parameters. So this difference between the two impulse response of the two ears give us the sense of spatiality of sound and help us in the localization of sounds. Okay, if you listen with the two patterns completely reflective patterns completely similar, there is no difference between the two ears. Okay, in this way, this condition, I have no sense of spatiality. I'm immersed in a sort of mono field. Okay. The lateral fraction, instead, the concept is similar, but it quantifies energy component of the sound field around your end. Indeed, lateral fraction is recorded with a microphone and a figure, an omnidirectional microphone, and a figure 8 microphone in the same position. Okay, in the center of a Cartesian plane. Omnidirectional microphone that capture all the sound around me, and a figure 8 microphone along the y axis. Okay, So, comparing the energy that we have along this axis, no, from my ears, y axis, to the with the total energy around me, I compute the lateral fraction parameter. Okay. Okay, so we need an impulse response with the omnidirectional component and the figure eight component along y-axis. Normally, today, in this day, we don't use two microphones to do this. We use, I use, and I will explain you in course part 3, applied acoustic to sound reinforcement. I will explain how to obtain all these kind of impulse response for sound reinforcement purposes, like binaural and others, starting from the recording with an Ambisonics recorder, grab and go model like Zilia for a high order Ambisonics, or simple first order like the Zoom. Okay, so if I open with a wave editor like Audacity, an impulse response obtained with the microphone with the Ambisonics system, we have something like this. We have a 4-channel impulse response, a wave file with 4-channel impulse responses. Okay, these are the impulse response, the signals that represent the B format, the so-called B format signal after the step of the ambisonic recording. Okay, we have the W component, that is the pressure component, the omnidirectional component. We have in this format, in this particular format of B format signal that is called FUMA. Here we have as a second file the X component. This is a vectorial component along the x-axis. This is the y component. This is the z component. Okay, so what we need to perform the lateral fraction parameter, I can, yes, here. So we need the omnidirectional component and the figure 8 along x-axis. This is my head, ears, nose, eyes. Okay, these two components, W and Y, and these are W and Y. So we can remove X, we can remove Z, and these are the two files that we need, the two impulse response we need. I export these two files. Yes, yes, okay. And now I go in ARTA, I import the impulse response of the y-axis, this. I set this as overlay because in ARTA I can't perform multi-channel measurement. Okay, so the strategy can be to use one impulse response as overlay and the other impulse response as the current impulse response. Okay, the overlay impulse response must be the figure 8 component. Okay, now I import again the W component, the omnidirectional component, and you can see here the different reflective patterns of the two impulse responses. So if I go now in analysis spatial acoustical parameters, I can say to evaluate lateral fraction. As also the note here say, as you can read, overlay peer impulse response has to be recorded with bidirectional figure of 8 microphone, while current peer has to be recorded with omnidirectional microphone. So estimate lateral fraction, and we see the values of lateral fraction here. So I can do another thing because best values for EACC and lateral fraction are 0.5, 0.7 for EACC, for interaural cross correlation, and 0.3 for lateral fraction. Okay. Indeed, if I, for example, I do this, I have yet to do something here in Crosslight. I start new. So is all clear. I import separate files, the left channel only, and I duplicate this. Okay, this is the copy. I export these two files. So if I perform, I start a new section. If I perform an EACC evaluation for the left channel and I set this as overlay, and I import the same impulse response. Okay, this. So as you can see, there is no difference between the two impulse response. So if I perform for example, the EACC, the result is 1 because the quantities are similar. Okay, this means that as I said before, the reflective patterns between the two ears that arrived and also that arrived at the two ears, because here in this impulse response I have the reflective pattern caused by the inner channel, the head, the human head, etc., plus the room impulse response. Okay, are similar, so there is no difference. There is no spatial audio here. Okay, I move in an anechoic chamber in this way. This is not beautiful for humans. Okay, So the good value is not the perfect similarity of the two ears, but a certain difference that we and a good value for EACC is 0.7. Now I want to show you something. I modify a little this impulse response, the copy. I put inside a notch filter at, for example, notch Q at 1000. Okay, I export this, export as a wave file, modified. I have yet exported previously. And so now I have yet the left channel impulse response saved as overlay. I now import the modified impulse response, the same impulse response, just with the notch filter, and take a look what happened. We have now two little differences between the two patterns. Okay, and so this traduce in EACC that is this. Okay, we have quite one for the band, for the other band, and we have less value for the frequency we have centered the notch filter. Okay, there we have the maximum in this octave, we have the maximum differences. Okay, I hope all is clear. Sorry for my bad English. As always, I'm trying to speak in English at the best of my possibilities. I thank you for the watching, and we can stop the recording. Bye.